Discover the latest advancements in network security at Intersect 2024, a virtual event from Palo Alto Networks where industry tech and cybersecurity professionals discuss how advancements in SASE are reshaping expectations. Topics include a secure enterprise browser, using SASE to secure and accelerate applications, and more. Intersect 2024 is available on demand now at intersect.paloaltonetworks.com.
Welcome to Heavy Networking, the flagship podcast from the Packet Pushers. I am Ethan Banks, and with me is Drew Conry Murray. If you can explain the difference between a switch and a router and also explain why there is no difference, you've found your tribe. Welcome. On today's show, Alan Kirby has joined us. Alan was there when the first Ethernet bridge was created at Digital Equipment Corporation and is going to tell the story of why and how it came to be. Alan, welcome to Heavy Networking. Thank you for joining us. And Alan, let's jump right into the conversation. We should start by setting some history here, especially for the younger networkers out there who have never heard of an Ethernet hub or wired up a vampire tap, that kind of things. Alan, would you explain to us what the first Ethernets were like? Because they weren't switched, they were shared bus, CSMA-CD.
Absolutely. So the thing you need to remember is, for context, the machines were much slower in the 1980s and the late 1970s. You know, the machines that I typically worked with had a clock speed in the low megahertz range. You know, the total amount of RAM might be, 8 megabytes. That would be a large machine. And the machines were still pretty expensive, which led to the continued use of time sharing, because the model of individuals having their own computer really hadn't taken hold at the time. And, most of those machines still had a lot of TTL logic in them. They didn't have a lot of VLSI or any VLSI to speak of. And so, memory was expensive. I mean, large-scale memory was expensive. $100 million per terabyte in about 1980, which, so it's maybe 6 orders of magnitude difference. LAN speed at the time, and as we talk about Ethernet at 10 megabits, is, roughly 5 to 6 orders of magnitude slower than today. And a serial line, if it was connecting a terminal, time-sharing terminal, to one of the hosts, might be running at 1,200 bits per second. So it was a very, very different world at the time. And I think, a lot of credit needs to go to the guys from Xerox PARC who envisioned personal computers, Altos, all connected by a thing that they had invented called Ethernet. And that kind of set the stage for what was to come. And when they first developed Ethernet, they envisioned a serial connection, which was really a thick coaxial cable, almost a half-inch in diameter. As I recall, I think it had 2 internal shields, and computers were connected to it with a cable from the computer to a tap, a so-called vampire tap, which in principle, allowed an installer to put a tap in while the network was still running. But what it entailed was using a tool to drill through the outer and inner shields to make room for a contact by this tooth or vampire to the central connector. And it was a thing to behold. There were markings about every 2.5 meters, or I think exactly every 2.5 meters, to ensure that the taps were placed on the markings so that the reflections would not be in phase. So it was not as simple as plugging in an RJ45 by any means. The ends were terminated, of course. It was a 50 ohm cable, and I think, as I recall, there were a maximum of 100 stations that could be placed on a 500 meter cable. And then, of course, the length of the Ethernet could be extended by using repeaters, which effectively retimed the signals and amplified the signals so that you had a clean signal after each repeater. Now, this was you could put repeaters into the Ethernet that would give you a length of the Ethernet of 1,500 meters. So it's a pretty lengthy local area network. Well, the original Ethernet actually ran at 3 megabits per second as designed at Xerox PARC. There was later a coalition of companies, Digital Equipment, Intel, and Xerox, which came up with a slightly speeded up version, a 10 megabit version that had the extent of 1,500 meters. And that was kind of a sweet spot. It really was, as I said, it was a sweet spot for the technology that existed in the early to mid 80s.
But one of the issues with these LANs is that was a shared medium, and so you had issues like collisions that you had to work around.
Absolutely. Because the signals obviously don't travel instantaneously from one end of the cable to the other, there is the possibility of collisions. And, if you've ever had a conversation that traversed a satellite link, you know that it's easy for people to talk on top of each other. And this is exactly what would happen on an Ethernet. So the collisions, there was a thing, it's essentially a collision domain, which is that, the time that it would take for a signal to traverse the cable to propagate from one end to another is essentially defining the size of a collision domain together with the minimum size packet. And so to ensure that you detect these collisions, essentially you need to make sure that the minimum size packet, if it was going to collide with someone else, had a chance to propagate the entire path on the cable. So that's kind of a summary of collision detection. And when a collision was detected, it was necessary for the sending station to detect that and to automatically retransmit the original packet. This was done after a combination of a random delay and a delay that was increasing exponentially with the number of continuous collisions. So in this way, Ethernet was kind of intended to be stable and provide fair access to all the stations on the LAN.
Alan, in the early days, Ethernet was not a sure thing. I came on the scene myself in my IT career in the early mid 90s, and even then, Ethernet was popular, but not the only thing. There was also FIDI out there, there was Token Ring out there, there was ArcNet, and maybe some other ones. Well, was the thinking at the time that one of these various I don't know, desktop networks, LANs, local area networks, maybe is the best way to put it. Was it the thinking that one of them was going to win or that coexistence was more likely?
Well, I think most people felt that there would be coexistence. And the main reason, I think, was that IBM had such a significant market share in the mainframe market that their favored technology, which was Token Ring, was likely to coexist with what DEC and Intel and Xerox were pushing, which was Ethernet, and that there needed to be a way for these to interoperate. And I think the interoperability was one of the reasons that the IEEE 802 standards were considered important within the industry. It would have provided more of an interoperability at some level. So yes, I think that the general expectation is that there would be coexistence of these technologies. I ought to note that the Token Ring from IBM, I think, ran at 16 megabits per second on shielded twisted pair. which was, of course, faster than Ethernet at the time, but not a whole lot faster. And so as we in DEC and probably other places were thinking about this, the feeling was that there needed to be something faster. And, generally, if you're going to make a major technology upgrade, you want to do it, at least an order of magnitude performance improvement. And so we were thinking it's got to be at least 100 megabits if we're going to replace Ethernet. And so a number of companies, including DEC, began working on FDDI, which was really oriented around multimode fiber, as you know, 1300 nanometers. And so that was kind of what we were expecting would be the next generation of technology. The problem was that we knew that the technology was going to be expensive, and things like the switches that were in place for failure recovery tended to be expensive. And the other problem with something like FDDI is that while an FDDI connection might have been really appropriate for one of the higher end machines that had a lot of throughput requirement, for a low end machine, it was probably overkill. And so, there was kind of a dilemma there. But to answer your question, yeah, I think the expectation was that there was going to be coexistence of LAN technologies.
Just commenting on FDDI being someone that was involved in, should we deploy this? Is this interesting technology for us? One of the things that put us off compared to Ethernet was fiber. We got to deal with fiber. It would be good if we knew how to polish fiber and be able to deal with that. That was part of it. Getting the fiber installed in the building was more costly than twisted pair. We were looking at Ethernet, and at the time, as fast Ethernet was coming out, 100 megabits per second, it's like, wow, we got a lot of speed here. The cable's way cheaper. We can even run it on some of the stuff we've already got in the building, and it just made FDDI kind of disappear because of that cost differential. And we were all in on Ethernet, and we're at the same time phasing out token ring. We also had IBM in one of the shops I was in, and there was some token rings were installed in the building for various needs. And that all became available. We could supplant token ring with Ethernet, and it's like, okay, we can just kind of move to this fast, less expensive solution that runs over relatively cheap, unshielded twisted pair. That's easy for us to install and maintain and test ourselves. Kind of became a no-brainer.
Yeah, absolutely. I think one of the things that was concerning also at the time was a lot of uncertainty as to how fast we would be able to make unshielded twisted pair run. Now we know that people take it up to certainly a gigabit, and I think I'm not quite sure, but I don't know if the 2.5 and 10 gig Ethernet links use, I think they're shielded twisted pair, aren't they?
The 2.5 and 5, you can do unshielded twisted pair, but there's distance limitations. And depending on how far you want to go, if I remember, I haven't looked at those specs in a while myself, but I know the further you want to go at those higher speeds, then you do need to get into shielded at some point.
Yeah, so there were a lot of unknowns as to how much you could drive reliably, especially unshielded twisted pair. And so that was one of the reasons for the continued investment in FDDI, because we knew that obviously, if once you run out of speed with multi-mode fiber, you can always go to single mode, which again is more expensive, but it's, trying to think ahead and read the tea leaves about how the technology was going to evolve.
Under the comment I'll say about unshielded twisted pair is just the different cats that have come out, and now we've got category 6, and just the number of twists per foot jumped so much that that also facilitates some of the higher speeds. But it's
it
thicker
does.
cable and all that too, and trickier to install and harder to get certified and more expensive and so on. But
yeah, I think there's Cat 7 and Cat 8 now too. So.
There are, and one or both of those are shielded, or at least some of the pairs are shielded, if I remember right.
Yeah.
So coming back to, sort of the bus style Ethernet we were talking about, we mentioned collisions. Were there other issues with this approach when too many clients were getting onto the same bus?
It's not so much the number of clients, but the overall utilization. So as the utilization went up, you would see the delay, on average, the delay is going to go up and the delay variance is going to go up. And so obviously, because the probability of collision goes up. And, there was a lot of fear, uncertainty, and doubt pushed by non-Ethernet companies. In particular, the people who were hawking real-time or hard real-time or soft real-time process control were pushing token bus. And, you can you can cover up a lot of sins with overcapacity. And that was kind of the approach that we wanted to take.
A great networking truth right there.
Yeah, absolutely. And so, but there were markets, particularly in the automotive sector. Token bus was seemed to be quite popular. But again, over time, with the introduction of switches and such, so-called real-time Ethernet has come into existence. So.
Let's pause for a word from sponsor Palo Alto Networks. You can discover the latest advancements in network security at Intersect 2024, a virtual event where industry tech and cybersecurity professionals discuss how advancements in SASE are reshaping expectations. Topics include the next chapter of SASE, securing workspaces on managed and unmanaged devices with a SASE native enterprise browser, mastering data security with AI, using SASE to accelerate application performance, and more. Intersect 2024 is available on demand now at intersect.paloaltonetworks.com. That's intersect.paloaltonetworks.com. And now back to the podcast.
So we need to get to the setup here where we talk about how bridging improve things. So one of the set of questions is about distance. And you mentioned distance in your earlier explanations of how Ethernet worked. So how did distance, the length of the bus, affect shared Ethernets?
Well, again, the longer, it's the longer the bus, the more opportunity there is for two transmissions to collide on the wire. And so, having a large collision domain, bandwidth distance product made it worse. And so trying to increase the speed of transmission of Ethernet. So if you imagine a CSMA CD Ethernet running at 100 megabits per second, you'd have to roughly reduce the span of that Ethernet by an order of magnitude. So that was a trade-off. Or the other alternative is you could increase the minimum size packet by an order of magnitude. And so collision detection is effectively what drove the difficulty of making CSMA CD faster. And as I said earlier, the 10 megabit, 1.5 kilometer, and I think 46 byte minimum size packet, that was kind of a sweet spot. So trying to imagine making Ethernet faster was going to be difficult.
So then you had an idea about how to sort of augment Ethernet to get beyond this shared bus problem. What was the germ of that idea?
Well, a couple of things. One is that the way Ethernet worked and the way token bus and token ring worked was that the LAN throughput could never really exceed the speed of an individual transmitter on the LAN, which is kind of problematic, right? I mean, Ideally, you'd like to be able to have a LAN whose throughput is a multiple of the speed of the individual computers transmitting. That was one issue. The other issue is that, not so much for Ethernet, which was a simple media access protocol, but the others seemed like it was a lot of work, a lot of complexity just to share a wire or a fiber. And, you know, I'm a simple guy and I like simple things. And so the thought was, well, why do we have to have a shared media at all? And that was the idea I went to Mark Kempf with. I said, why don't we just, have some switching and we can avoid, the need for CSM ACD. We don't need that. We can just connect these individual hosts to a switch. And the problem with that idea is that it never would have gone anywhere because it would have ignored the installed base of Ethernet and Ethernet devices. So that germ of an idea is what I went to Mark with and said, hey, is this an idea worth pursuing? I thought it was. And, it ended up that he had already started thinking about this direction earlier. But when I prompted him to really come up with the learning bridge, which he actually did the following day after I spoke with him.
The key words, Alan, I think that you haven't said yet, but I think I want us to explain to the audience here are store and forward. On a shared bus, there is no storing and forwarding of Ethernet frames. It's as you described it early on. The first iteration was literally a wire that everyone would tap into and share. There was no electronics or circuitry there that was analyzing frames and making any decisions about them. You got your chance to speak on the wire, put your burst of electricity on there, and the receiving station would see their MAC and oh, that's for me, and pull it and do something with that data as it pulled it off the wire. But bridging or switching requires store and forward. Can you explain that?
So effectively, think of the bridge as another station on the Ethernet, and it would effectively receive all the packets that were sent on the Ethernet, independent of which machine was the sender and which machine was intended to be the receiver. So it would receive all of those packets. It would remember on which Ethernet it received a packet, and then it would forward appropriate packets, if necessary, to the other Ethernet to which it was connected. And so it effectively made use of local memory bandwidth within the switch to save those packets and to forward them as quickly as it possibly could. And, this extended from, a bridge connecting two Ethernets eventually to what we see today, which is effectively every host computer connected to its own dedicated switch port, where that memory bandwidth or crossbar or whatever switching technology is used is substitutes for that shared wire.
So I want to make sure I understand this sort of first iteration of this device. You had, say, like one island of X number of computers that were all on a shared wire, and then a bridge, and then another island of shared computers all on a shared wire. And this bridge was literally connecting those two islands.
Yeah, I think it's important to know that the initial Ethernet bridge was only connecting two Ethernets. But we knew from the beginning that having a bridge or a switch that would connect multiple Ethernets together would be much more desirable over time. The problem was that receiving all back-to-back packets, minimum size back-to-back packets from an Ethernet, and they could arrive at about 15,000 per second from each Ethernet. All of those had to be processed, and the learning that was required was, all right, I've received a packet from this source MAC address, and I need to remember which Ethernet that source is on. Mm-hmm. That was challenging with the technology of the day. And that was the thing that was, I think, surprised people about, Mark's bridge. Basically, that it could process minimum size back-to-back packets. Prior to that, no one had been able to come close. And I think one of the reasons was that routing was a more complex process than switching or bridging. Mark to make this work, Mark chose some of the best technology of the time, which was a Motorola 68000 microprocessor. But even with that, he had to design a PAL, programmable array logic based binary search engine with 48-bit wide static RAM to do these binary searches and insertions. It was it was very challenging, but he was able to make it work. And Mark was one of the best hardware engineers that I've ever known, and it was a brilliant design. I remember, and I can't recall whether it was for this product or a different product, that I got a call from Gordon Bell, who was a senior exec at DEC at the time, asking why we weren't using the T11 microprocessor, which was DEC's internal PDP-11 chip. And to Gordon's credit, he listened to reason. He didn't push unreasonably on the use of the T11. So the Bridge product and another product used the Motorola 68000.
I can see how that could have been an uncomfortable conversation about why aren't we using our own internal hardware on this.
Dad wants to know.
Yeah, but he listened to reason, and one of the reasons, in fact, was the internal transfer cost of the T11 was higher than the cost of this Motorola 68000. So
this is, how long did it take Mark to come up with this design and actually get a working prototype in place?
Oh God, I don't recall. I believe it was a matter of less than a year.
Wow.
And it's the PAL design was was complex. And if you in the IEEE Spectrum article, they had a picture that we took when Mark visited here a few months ago of the logic board of the Landbridge 100. And you can see there's a lot of TTL logic on there in addition to the PALs and the Motorola 68000. So this was not an easy device to design. Mark spent a lot of time sweating over those over the timing analysis of that design.
So did DEC sell a lot of these products, the DEC Bridge 100?
The answer is, I believe that it ramped up over time, and I actually can't tell you the volume of the Landbridge 100 over time. What I can tell you is that people began to start thinking differently about Ethernet, but it wasn't like lightning struck the moment we introduced that product.
Well, that's actually a good question. So when the first Ethernet bridge went out the door, what was the reception by the industry?
I think, in general, I think the reception was, ooh, this is a great enhancement to Ethernet. It didn't stop work inside of DEC on FDDI. And I think one of the reasons for that was that a lot of people were still skeptical about the speed of Ethernet on shielded twisted pair or twisted pair. And so I don't think the impact was fully appreciated at the time. Our group later built a product called GigaSwitch, which connected a bunch of FDDIs together and also supported Ethernet. So once GigaSwitch came out, we could have an extended local area network that was comprised both of FDDI and Ethernet. And I think that got people thinking more about, ooh, maybe we can take this bridge idea or this switch idea even further.
When we talk about loops, Alan, Ethernet loops still a potential danger and a concern? And how did the solution to loop prevention come about, and how did that play into bridging as it was becoming more popular?
Sure. So the issue is that if you connect, in the simplest case, say you have two Ethernets um, connected with two bridges. Well, that's going to cause a problem because of the way learning is done. One would see a packet appear on both sides, and so you wouldn't know where that source computer was. Was it on the Ethernet on your left or the Ethernet on your right? So we knew that that was an issue, and we had wanted to solve it. But my boss at the time, Tony Locke, insisted that we prevent this kind of misconfiguration from taking down the LAN. Obviously, it's an important, safety feature, no question about it. But as it turns out, I only found this out a few months ago, is that both Mark and I felt that, in a pinch, the product could ship without this. And yes, bad things would happen if the network was misconfigured, but that this technology was so important to get out in the market that we felt even if we couldn't solve the problem, it should ship. But then, nevertheless, we all wanted to solve the problem, but Tony really pushed it, and I'm glad he did, because a number of people, including myself, had ideas on how to solve this, but Radia Perlman came up with the absolute best approach, which was the spanning tree protocol. And, everyone agreed that this was the best approach. And so that's what we implemented. And we have reports that it certainly did save some customer LANs from going down. So, we knew that in the end, it was good that we had implemented spanning tree.
So Radia Perlman was an employee at Digital Equipment at this time?
Yes, she was. She was an architect in the architecture group. I ran the advanced development group. There was another parallel group called the architecture group, of which Radia was a member. Interestingly, go ahead.
No, go ahead.
Oh, I was going to say that apparently some inexpensive consumer switches these days don't implement spanning tree. And I believe that there are some commercial ones that allow it to be disabled. And, I don't know whether you or your listeners know what fraction of companies might turn off spanning tree. But that's an interesting question to me. I don't know the answer to that.
And it's even more complex than the way you described it, because there is some amount of FUD and disinformation around spanning tree that I've run into with different folks over the years, where they think spanning tree causes loops. Oh, you got to shut off that spanning tree. It causes loops. It's like, wait, you don't understand what's going on here. Spanning tree prevents loops. You've got to configure it correctly. You've got to have your cabling and topology appropriate. It certainly does not cause loops.
Right.
There's some of that. And of course, because of the rise of layer 3 networks and rather than such a heavy reliance on layer 2 networks, there are questions of, do we actually need spanning tree, in this topology, or is it safe just to shut it off and not have BPDUs roaming around the network if we don't actually need them, if it's been constructed in a way, or should we leave it on as a safety feature, just in case kind of thing? So it's complicated, I think, is the answer, because of what modern networking has evolved to.
Right. Interesting. You mentioned the increasing use of layer 3. Layer 3 had historically been a process. Routing was a process that tended to be a lot slower than switching, and with the increased use of VLSI in routers. That's less of a problem than it was. Nevertheless, switching seems to have a life of its own and continues. So,
Hmm.
Getting back to Radia for a second, I'm just curious, was she aware of or involved in this project, sort of at the outset, or just sort of like, oh, let's go ask Radia down the hall if she has any ideas about this as things developed?
so the same day that, so the day after I mentioned the switching idea to Mark, and Mark came up with the idea the following day. I had gone to three levels of management and got approval to, one, build a prototype, and two, that there would be a product that would follow
Mm.
if the prototype was successful.
Hmm.
And within a few days of that, my boss, Tony, kind of challenged a lot of people in the group to come up with a solution to the packet looping issue. And, one of the people who was challenged was Radio.
Hmm.
And, you know, being a pretty smart person, it didn't take her too long to come up with a good solution. And so um, it really didn't take long. And, once the spanning tree protocol uh, had been specified, the implementation was really not that difficult.
So now that you've got this Ethernet bridge, did that sort of kind of was this the death knell of FDDI token ring other competitors in the land space?
It really was not. And I think part of the reason was the expectation that the the speed of twisted pair would end up being limited much more than it actually has been.
Mm.
And so the expectation was that we were still going to need the ability to have individual stations, um, transmit and receive at 100 megabits and beyond. So, um, yeah, I don't think the impact of switching was fully appreciated at the time. And again, you know, with the initial bridge being a two Ethernet device rather than an N port device where N is greater than two, the impact of switching was not appreciated, I think, for probably a number of years.
Yeah, what was that sort of ramp up from bridging to switching, where instead of shared medium, you're plugging devices directly, each device gets its own cable into a port on a switch?
Well, I think it probably happened certainly by the time gigabit Ethernet was introduced.
Hmm.
But I don't recall the exact timing of that. Um,
As someone who was living and breathing that, this is I would say, mid to late 90s into the early 2000s. Buying a switch where every port was switched was costly. So if you were comparing a hub versus a switch, it was a significant jump in budget. And so that for a long time, that was the decider. Do I want this, or can we live without it? Is the performance going to be adequate for this kind of a traffic mix? If we have maybe we or there was a compromise design where you'd have a switch and a bunch of hubs hanging off the switch. So the switch would be like a giant multi-port bridge with a bunch of shared Ethernets hanging off of it in the form of
mhm,
smaller hubs, just
right.
for the cost efficiencies of it. And again, that took years. And then eventually, I kind of remember this. There was like a tipping point where it got to be, oh, for a very nominal increase or almost the same port for port cost, I can buy a switch. I'm not buying hubs anymore. My days with hubs are done. And there was actually a movement to retire the hubs and begin. There was a number of projects I was a part of. It was like, we're replacing the hubs with switches because we can do this now.
Right.
And life was a lot better. And then it was just the standard. I don't even know if you could buy a hub now if you wanted one. I mean, that's been years since I've seen a hub as a productized thing.
Was that?
Yeah, and I think it probably depended to some degree on the performance requirements of the individual installation. I know that GigaSwitch was certainly very popular with a lot of the big science labs, Livermore and CERN and Sandia. They were all interested in GigaSwitch technology. But as you say, I think enterprises that had, more modest performance requirements would certainly make a decision based upon, some formula of performance and price. So,
Yeah.
price performance was important. And as switching VLSI, dedicated switching VLSI came into existence, chips are cheap generally, and so it was only a matter of time.
Did digital equipment have a plan to evolve along with the market from, bridges/hubs to switches? Was that sort of in your roadmap or in the company's roadmap?
Well, I mean the products that we had, were the Ethernet bridges and GigaSwitch and other bridges were built, but DEC really started to implode in the early 1990s, and so it went from a company that had about $800 million in annual revenue on networking gear to when at the same time Cisco had $8 million in revenue. DEC just shot itself in the foot, and it never really had the vision to to see what the networking business could be. I mean, DEC had different interconnects for connecting clusters of access together. It didn't use Ethernet. It didn't use FDDI. And a lot of that, I suspect, was simply because of the way the company was organized. So the technology kind of reflected the way the company was organized.
Alan, would you have guessed that Ethernet would have such longevity? We're recording this in 2024, and now we've got 800 gig products using coherent optics, and 1.6 terabit Ethernet is being researched right now. It's mind blowing.
Not really. Essentially, Ethernet has become a kind of a marketing name for technology which is fundamentally different to the technology that was originally called Ethernet. And so on that basis, I would say no. However, the technology of high-speed switches connected to hosts via dedicated switching is certainly what I and others later did envision. But no, I would not have guessed that it would still be called Ethernet.
What do you feel is different between sort of the Ethernet that you were working on and what is today called Ethernet?
Well, I think with the exception of some of the slower Ethernet chipsets, collision detection is gone, half duplex support is gone. And so I think part of this is kind of a philosophical question. If you change all of the individual parts of a thing over time, is that thing really still the same thing?
Right.
I sort of have this feeling along those lines with something like the Ultra Ethernet Forum, which is, trying to design Ethernet to support the constraints of AI workloads. And it's essentially trying to make Ethernet, a lossless medium when it's not. So yeah, I guess I feel the same way. It's Ethernet on the cover, but what's under the tin.
Yeah. I mean, Ethernet still provides a hugely useful abstraction to the protocols that are above it. And I think it would be a heavy lift to get rid of that abstraction.
Well, let me ask maybe a parting question here, Alan. That's let you dip into the philosophy a bit more. Should Ethernet have lasted so long? Do you think the industry at some points just kind of have to move on to another local area transport? And I could ask the same question of IP and the TCP/IP stack as well.
Well, I think that's a hugely interesting question, and one of the things I would suggest that you and your listeners might be interested in is Google a talk made in '06 by Van Jacobson. It's a talk that he did at Google about moving away from IP and TCP to something that was called named content networking. And it's a huge change of mindset. If you're not familiar with it, it has some great history about how things evolved from circuit switching to packet switching, and how it might evolve to a different paradigm. So I think if that in that paradigm that he describes, that I'm somewhat familiar with, I think Ethernet still has a place. That same useful abstraction could be useful in named content networking, for example. But I think it's going to change. It would require a pretty significant change of mindset to conclude that the service abstraction of Ethernet is not valuable.
Yeah, it does feel like the industry juggernaut behind Ethernet just rolls on and changing because of the inertia of it and the stickiness of it. Changing out of it seems it's hard to imagine how we could move to something else at this point to me.
Yeah, and part of that inertia is some of the large companies that are involved in producing switches and routers. But yeah, there is a lot of inertia there, no question.
Alan Kirby, this has been a fantastic discussion. If people want to follow you on the internet or connect with you, I know you're on LinkedIn. Are you out there anywhere else?
I tend not to be a big social media guy, so LinkedIn is the place. So.
Well, for those of you that are listening, this talk came about because of an article that Alan contributed to IEEE Spectrum. We've linked to it in our newsletter in the past, and we'll link to it in the show notes at packetpushers.net. How DEC engineers saved Ethernet, how engineers at Digital Equipment Corporation saved Ethernet. And that was the story of the bridge. That picture that Alan mentioned of the circuit board with he and Mark is on there. And again, just Google that or hit the show notes and link. And it's an article. It's a great read. And our thanks to Alan Kirby for agreeing to come on the show today, because not everyone loves being on a mic, but Alan was up for it to help preserve networking's critical history. And thank you for listening to Heavy Networking today. Drew and I want to hear from you about this in every episode. If you've got something to share with us or a question to ask, hit our follow-up page at packetpushers.net/follow-up. And we have many other shows in the Packet Pushers lineup. If you only listen to this show, which is Heavy Networking, you are missing out on Day 2 DevOps, IPv6 Buzz, Network Break, Packet Protector, Heavy Wireless, Network Automation Nerds, and more. Each and every podcast is hosted by industry practitioners or seasoned analysts who share information for your professional career development. Search for Packet Pushers in your podcast client to see all of our shows and hit the subscribe button. Last but not least, remember that too much networking would never be enough.